Okay, fine. So today we are going to see the topic for drift velocity. Okay, drift velocity of electrons, and we will also see what is the origin of resistivity. Okay, okay. So let's start with a quick revision of the previous topic, that is Ohm's law. Okay, so if you recollect what is Ohm's law, okay, we will quickly define this. Ohm's law. So this is defined as the amount of current that flows in a given wire, right? And that current is proportional to voltage across the ends of a conductor and is also inversely proportional to resistance of the conductor. So in short, we can say that I is proportional to voltage and I is inversely proportional to the resistance, right, across which the current has to be flown. Right? So this means that if you have a battery of a given voltage, right? So I say V is a constant value. Okay. So let's consider two circuit. Right? You have a battery, you have a resistance. Same way you have another battery, right? And you have another resistance. So what I do, I just rename this. That suppose this is R1 and suppose this is R2, and I say that R1 is greater than R2. Okay, so let's take the example that it is 10 volt, right? So this battery is also 10 volt. Okay, now if R1 is greater than R2, obviously in this case what we can write is that current in the first circuit will be I is equal to V upon R. So this value will be 10 by 20, right? Or you can say it is 0.5 ampere. Similarly, I2 you can have, that is 10 by 10. I'm taking the example that R1 over here is 20 and R2 over here is 10. Okay, so I will have 1 ampere. Okay, so in short, what we can say is that in a circuit with a given constant resistance, okay, so let's say if you have a constant resistance, so R1 is equal to R2. Okay, so you can write I is equal to V upon R. So in a circuit with a constant resistance, so I say resistance is constant, R1 is equal to R2. Greater is the voltage applied, right? So large, if you say V is equal to, suppose I say, let's say V is, if you increase the value of C, voltage, so suppose that is 10 volt. So that means let's R is equal to 1. So I will be 10 ampere. And if you increase the voltage say to 40, right, your current will be 40 ampere. Right? So for constant resistance, if you apply the higher voltage, greater will be the current flowing in the circuit. Okay. Now another important point to be remembered in this Ohm's law is its validity. This is only valid for metals. This is only valid for metals. Okay. However, we are having an exclusion of tungsten. Right? Tungsten is the metal. Right? So you will have tungsten. This is the only metal whose resistance is actually changing with temperature. Okay. That means if you increase the temperature, this is the same tungsten filament that actually we are using in our bulb. Okay, for a light. So if you increase the temperature slightly and slightly, okay, then also there is change in resistance. Okay, other metals also they are going to show the variation in resistance with respect to temperature, but there is a particular limit that in that particular temperature region the resistance is almost constant. So most of the metals they show, so in a specific temperature region, so I say this is temperature region. Okay, so for this temperature region you have a valid Ohm's law. Okay, that means resistance is not changing. Resistance is not changing. Where in this particular temperature range. Okay, fine. So you can see that Ohm's law is valid for constant temperature, or say till a particular certain temperature limit. Okay. Now let's quickly define what is 1 ohm, because we have actually been using now, right? Because now we say that V is equal to IR, or I is equal to V upon R. So we will define three different terms. That is, first is Ohm's law. Okay. So sorry, not Ohm's law, it's 1 ohm. Right? So what is this 1 ohm? You can define this as resistance, right? You can define this as resistance that will produce a potential difference. Resistance that will produce a potential difference, that will produce a potential difference of 1 volt, where across the resistance, across the resistance, right? For example, you have the resistance, right? Okay. So what is the value of this resistance? Okay, so that potential across this point and potential across this point, right? If you measure the difference between them, you will get a value of 1 volt difference. Okay, and the current passing through this should be 1 ampere. So you can define in a simple language that 1 ohm is nothing but the resistance that will produce a potential difference of 1 volt across the resistance when we want to draw or we want to flow 1 ampere of current. Okay. In a similar manner, you can say 1 ampere, right? 1 ampere. So that means you are talking about current. Okay. So this is nothing but this is the amount of current. You will say this is the amount of current that flows, that will flow through a resistance, flows through a resistance, say R is equal to 1 ohm. Okay. So the amount of current that will flow through 1 ohm resistance and produce a potential difference of 1 volt, right? So you current that is required to flow through this 1 ohm resistance and to produce a potential difference of 1 volt across this resistance, that is called as 1 ampere. In a similar manner, we will also define 1 volt. Okay, so 1 volt, we are talking about the potential difference. Volt is the potential difference between two terminals or 2 points, 2 reference points. Okay, so you will say that it is the difference in potential, right? Difference in potential where across a resistance. So you have a resistance. Okay, so potential difference across point A and point B, across the two ends of the resistance. Okay, through which I am allowing a current of 1 ampere to pass. Okay, so that is, it is simple. In simple terms, you will say that difference in the potential across 1 ohm resistance through which you are allowing to pass 1 ampere current. Okay, fine. And quickly we will see also, we have see that now this resistance, right? This resistance is proportional to length and this resistance is inversely proportional to area. And we write the combined formula as R is equal to rho L by A. Okay, where R is the resistance, rho is the resistivity, L is the length of the wire, and A is the cross sectional area. Okay, where rho is the resistivity. So resistivity, you can define it as, resistivity is what? That is resistance of a wire across its length. So if you take a unit length, right, what is the resistance that you are going to face if you want to pass current through across this 1 unit of length or any length? So you take the reference as unit length. That is called as resistivity. And if you take resistivity inverse, so 1 upon rho, that will be equal to sigma, that is the conductivity. Okay? So conductivity and resistivity both are related. Okay, okay, fine. I will repeat for you again. Okay? That resistivity and conductivity both are related. Okay, so if you just see over here, you write rho is equal to R into A by L. right, from this equation. Okay. This is resistivity. Resistivity. This is actually a material property, right? Okay. So this is nothing but your material property. So I call this as material property. Now, what does that mean? That every material will have their own value of rho. For example, you say that you have aluminum, right? You have, say, silver, and you have gold, right? Resistivity of this will be different. Resistivity of silver will be different. Resistivity of gold will be different. Okay, that way. Okay, so this is a material property, and each value of rho is a standard value that is provided in the data sheet. Okay, so we are talking about the resistivity and conductivity. Okay. So resistivity rho is written as 1 upon sigma, where sigma is called as the conductivity, or you want, you can write it as sigma is equal to 1 upon rho. That is one and the same thing. Okay, so they both are interrelated. Okay. Second thing, if you talk about, so this is resistivity. If you talk, that is actually ohm into meter, right? If you talk about, it is across the length, right? Whereas conductivity, that is defined, or that is having the unit of mho, right? That is having the unit of mho. Okay, fine. So let's move ahead. Okay. One more addition in that. So when you are writing R is equal to rho L by A, okay, just to understand, if you, right, resistivity is the material property, so this is a constant. So for example, if you take a wire of aluminum, right, so you take one wire of aluminum, you take say second wire of aluminum, say this is length, right? Let's say the resistance, right? So what will, so to this will, so say you will be having one, okay, one, and area, whatever the value of area is, A1, but I have taken the wire from the same material, right? That means dimension are same. So that means rho value and the area value, that will be same. Okay. So what I can say now is that I can simply write it this way, that first one, resistance for the first wire, that will be rho upon A, and R2 will be rho into 2 upon A. So if you take the ratio, right, so you can say, you can directly write it over here, R1 upon R2. So this will be this, divided by 2R2, right? Okay. So here you will have equal to, so R1 upon R2. So this rho and rho will cancel out, rho and rho will cancel out, A and A will cancel out. So this 2 will go over here. So you will get 1 by 2. Okay. You will get 1 by 2. Okay. So then in short, you say that resistance will increase if the length is increasing. Okay. Now let's say, okay, we start with a new topic, that is drift of electrons. Drift of electrons. Now we are already aware that if you have any material, right, semi-solid material, so you have lattice over there, right? So lattice is what? You have periodic arrangement of atoms, right? You have all these atoms sitting at these points. Okay. Okay, fine. So what I say is that, now what will happen, that suppose let us consider this is metal, okay, for simplicity. Okay, so we already know that metals, they are possessing free electrons. They are possessing free electrons. Free electrons. Now, what do you mean by free electrons, or why they are free? Because of the thermal energy, that is 3 by 2 K beta T. Okay, the thermal energy that is provided from the room temperature. Okay, Fine. So that means outermost electrons are free to move in the lattice. They cannot come out of the body, but they can move in the entire body. So let's say that you have this red color electron. Okay. Now we say one more electron, one more electron. Now you have this large lattice. Okay. So these electrons, because of the thermal energy, because of this thermal energy, they actually go this way, 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 this way. Right? There is no particular path. Okay, that is called as zigzag motion or the random motion. Okay. Now, basically, what happens over here is that if you see, these are actually positive. The black ones, they are actually the positive ions, right? These are actually the positive ions because they are actually the ions, right? Electrons has been removed from the outermost shell, so that nucleus and that core has got positive charge. Okay. Now what happens? That because of this random motion, right? Electrons are actually colliding. Electron, right? They collides with the positive ions. Positive ions. Okay. Right. Now there can be probability that electron can be captured, right? Because that is electron and it is a positive ion. So the electron can be captured. However, you can say that the velocity is high and they actually have the fast collision, and that is elastic collision. Okay. So I say elastic. By elastic, I mean that the kinetic energy is conserved. Okay. Kinetic energy is conserved and momentum is conserved. Okay. So electron will collide with the positive ions, and post the collision, after the collision, okay, these electrons are again scattered in the other direction. That means if electron was earlier go this way, it was moving this way. Suppose this was a ion, right? So it came this way, now it is moving this way, right? Here it is facing another ion, it can go this way, it can go this way, it can go this way, right? So there is no particular direction of the electron after collision. Okay. But you can say that because it is an elastic collision and the mass is not changing of the electron, so you can say that this elastic collision will provide same speed to the electron after collision also, right? Because it is an elastic collision. Okay. Now, if you say that you are tracing the entire zigzag path of the electron. Okay, it is moving from point A to point B, for example. Now, what will happen over here? Okay, that if you are tracing this entire path of the electron, you will find that average velocity of this electron is actually 0. That is because of the different direction, because of the different direction of the electrons, right? As I told that it once it go this way, it can go this way, it can go this way, it can go this way. There is no particular direction. So you can say that average velocity is 0. Okay, fine. So let's example, you can assume that suppose there are n number of electrons. Okay, and you can say that velocity of each electron, right? Velocity of each electron. So I say Vi, I am defining I as the number of electron, right? So ith velocity of the ith electron is Vi, right? So I will write I is equal to 1, 2 until n number of electrons. Okay. So what I can write is that the average velocity as this 1 upon n, summation of I is equal to 1 to capital N, and Vi that is equal to 0. Right. So in this way, I'm just representing that this is the average velocity. Okay. Now, important point is that all of this motion is taking place in in absence of what? Of any external force. Right? There is no magnetic force, there is no electric force, right? Okay. So let's say that I am applying, right? I am applying an external electric field, right? You write E external or you can write E, that is all right. Okay. So you are applying this external electric field. Okay. So you can apply how? Suppose this is your body, right? You can simply connect this with a battery, right? Obviously, now the direction will be from positive to negative. That will be the direction of electric field. Okay. So now let's understand that when you say external electric field has been applied, okay, I'm clearing of this. So let's say, fine. So you have applied this electric field, say E. Okay. Now this electric field, right, that is going to apply a force of Q into E, right? So you will say that this is the electric force that is being applied on the electrons, because we know that this is normally F is equal to Q into E, that is the normal force, electric force. Okay. So hence an external force will act on each electron, and electrons will be now forced to move in a fixed direction. Right now, this electric force will actually, these electrons that were moving this way, this way, this way, okay, it will actually now force to almost, say, for simplicity, if the electric field is high, you will get almost a directional motion of electron. So that means earlier electron was going this way, this way, this way. Now this electron is going on this linear path. Okay, this is one thing. Why this is? Because velocity. Okay, now let's see. It has changed its path because of the external electric field or external electric force. Okay. Now, because the velocity is changing, right? Because now see, this was the, you say that this is the first direction, right? Initially, the electron is going this way. So, post collision with the ion, it has moved this way, right? We have said that the speed is same, right? We are talking that in the absence of external electric field, the speed is same because of the elastic collision. Fine. So speed is same, but direction has changed. Okay, fine. Now, because of this external electric field or external electric force, this is now moving in this particular direction. That means earlier the direction was this, the first direction, now the direction is this. Okay, of the first path only path. So this path has become this way. Okay. So what I mean to say is that the velocity will change, right? So that means earlier it was V1, now it is going to V2. Okay. So that means there is a change in velocity. And wherever there is change in velocity, you will say that there is acceleration, right? Okay, acceleration. So because there is change in velocity, and this change in velocity, right, I can represent this as F is equal to m into a. That is normal law of motion, that whenever there is motion, you are going to write the equation in terms of F is equal to ma. What is the force applied? That is E into E. Okay, so that is equal to m into a. Okay, fine. So now suppose I say this was our material, right? And we have applied a battery over here. Right. Okay. So now what will happen? That electric field is from this plus to minus. That is all right. Now what will happen? That electrons over here, they will drift. They will now start moving in the opposite direction. Right? Because we already know that electron move in the opposite direction of the electric field. Okay. So in short, what we can say is, okay, so over here, we can say simply that electron is drifting in the opposite direction of the applied field, Okay. So I can write from here that this electron, E is the charge of the electron. So I can write this as minus E into E, that is equal to m into a. Or I can say that acceleration is how much? That is equal to minus E upon m. Right? So this is the acceleration acquired by the electrons, right? Earlier it was not so, right? So this is the effect. You can see that this is the effect of applying the external force. Fine. So we can also understand this in a better way, okay, in a more detailed fashion. So let's say that just after collision, I say just after collision, okay, So just after collision, what I'm doing is I'm considering that the velocity of the electron is suppose vi. Okay, vi. Okay, now because the system has accelerated, right? Because the system has accelerated, there will be some change in the velocity. So let's say because here the velocity is increasing, it is going in a particular direction. So I say that velocity is increased. Okay, fine. So let's say this way. So I will say that the final velocity attained by the electrons, I say I the electron, okay, at a time time t dash. Okay, I'm denoting t dash. Okay, so this final velocity, okay, I can write it over here, final. So this final velocity of the electron is equal to what? Initial velocity, right? In the absence of field, now it has gained some velocity v, right? I'm simply saying that because after collision, some velocity change is there, and we are taking that as positive. Okay? So obviously, the change will be positive, right? So what I am writing is that vi, that is equal to vi, that is the initial, that means the velocity in the absence of electric field, right? Minus e into e upon m into ti, right? This we have written this bracket term, right? That is acceleration, right? So if you write acceleration into t, right? So if you write acceleration into time, this will give you velocity. Okay, so let's understand ahead that we are interested to see the change in the total average velocity, okay, in the presence of electric field, right? So this vi, capital vi, that is the average of all the electrons in the presence of electric field, right? So I say that vi is the average of all electrons, okay, at a given time, at a given time, at a given time. Okay, but we know that average velocity of small vi, right, that is in the absence of electric field, that is zero. Okay, so what I'm doing is let's move ahead. I say summation of vi is equal to zero. Okay, so important point to note here is that the collision are just completely random, right? That is, no time is fixed between each collision, right? If you take one collision is occurring now, right, there is no surety that after a particular, say, 1 second or 2 second or 3 second or some millisecond, after a fixed interval of time, collision is going to take place, right? So that time is not fixed, okay, because that is a random collision. Okay, so what we do is we define a new term, okay, of the average time. Okay, so no time is fixed for the collision to occur, so we will consider the average time for collision. So average time for collision, I will define that as the time tau. I will denote this as tau, time required for successive collision, right? Time required for successive collision, one after another. One collision takes place, after a particular time another collision will take place. Okay, now this is actually a mean time. This is a mean time. Okay, this is not an exact time, this is a mean time. So in terms mean time means I can say that suppose of average time is tau. So that means a collision can take place just before tau also, just after tau also. Okay, for example, you say tau is equal to 5 seconds, for example, right? So you will say that it can happen at 4 seconds also, it can happen at 6 seconds also, but the average will come as 5. Okay, so that is actually defined as tau, that is the mean relaxation time or the mean collision time. Okay, fine. So we are interested in calculating what the average velocity. So I will define this average velocity as Vd, that is also called as the drift velocity. We will see it. So I call Vi, capital Vi average, that is equal to, I'm taking the average of the previous equation. If you remember, that was what? Vi, right? In the absence of electric field, average of that minus E into capital E upon M into average of time. Okay. So let's write it this way. So this average, so I will write Vi bar, average of all the velocities of the electrons, that is given as, now the average of this is 0 in the absence of electric field. So this is 0 minus E upon M, and I'm replacing this average time with tau. Okay, that is called as the relaxation time or the mean collision time. Okay, so what I will get is that drift velocity Vd, drift velocity, that is equal to minus small e, or we'll just rub this. Okay, so you can write it as Vd, that is equal to minus of E upon M into tau. This is the drift velocity. That means the average velocity gained by the electrons in the presence of external electric field. Okay, and this is called as drift velocity. Drift velocity. Okay, now important point is, if you just observe over here, right, that if you have Vd, that is equal to minus of E tau by M. Okay, now I'm not having factor, direct factor of time, rather I am having tau, right? What is the importance of this, right? So this actually says that if you try to replace tau with time, right, so time, that is going to increase continuously, right? Because time, it is 1 hour, then it is 2 hours, then it is 3 hours. So time is going to increase, right? So if in this particular equation, right, if I place t instead of tau, what will actually happen? That this charge is fixed, right? Charge is fixed, electric field is fixed, mass is fixed. That means if you have connected a material of metal, right, with the battery, right? So what you say is that the electrons over here, right, that will be drifting in this direction. It can gain a velocity, right, Vd, that can go as to infinite, right? If time is, because time is going to increase. If time is increasing from 1 second to 1 hour to 1 day to 1 year, right? So that means your electron will gain infinite velocity. That is practically not possible. So that's why we actually say that it is not t, we replace it with tau. We cannot have t over there. Okay. So this is not depending on time. Okay. But this is another thing. So what we will do, we will stop over here, okay, and we will just see the next related topic with this, okay, that is the number of charge carriers, that are being transported from one part to another. In sense, suppose this is your material, right, this is your metallic body, okay, so you have this area, right, or you can say that you have a tube, right? So what you can say is that suppose the water is passing from this side, right? So this is the cross-sectional area, right? So given a particular data of time or say velocity, right? I will ask you that what is the volume of water? What is the volume of water that can actually cross this particular tube and flow out, right? So for that we will require some particular data. Say at least the volume should be required. What is the volume of the pipe, right? What is the velocity? What is the force in that? So we will, in the next class, we are going to see what are the number of charges that will pass from this end to this end, from this end to this end, or right left hand to right hand, okay, in a given interval of time. Okay, so we are closing this chapter, this session over here, and we will meet in the next class.